When a shooter moves laterally, their entire musculoskeletal system engages in a complex balancing act. The challenge lies in maintaining the sight alignment required for accurate projectile flight while navigating terrain. In a static position, the physics of shooting are highly controlled. The shooter aligns their skeletal structure with ground reaction forces to create a predictable platform. But normal walking disrupts this geometric advantage. Bipedal locomotion is a highly volatile process. Every time a foot strikes the ground, it generates a kinetic shockwave that travels up through the ankles, knees, and spine. Even with perfect trigger control, a shooter must contend with these internal microtremors. If the skeletal geometry is compromised by movement, those shocks transfer directly to the muzzle of the firearm. Shooting accurately on the move requires the body to actively override natural bipedal mechanics. The shooter must force their limbs into an engineered weapon platform. Analyzing this platform requires an investigation into internal kinetic stability, the external ballistics of moving projectiles, and the metrics of physiological failure. This degree of precision demands a deliberate biomechanical state, where the shooter must consciously manage multiple physical variables simultaneously. Static stability relies on passive alignment with gravity. Dynamic stability requires the active management of momentum. This management is achieved through biomechanical damping. A moving shooter must use their knees and ankles as mechanical shock absorbers, dispersing the impact of each step before it reaches the torso. These shock absorbers facilitate a center of gravity glide. A proper glide keeps the torso parallel to the ground, minimizing the vertical sine wave pattern of a normal walking stride. Above this glide plane, the upper body functions as a decoupled turret. By maintaining latitudinal isometric tension, the shooter locks their torso and firearm into a single structure, isolating the aiming eye from leg movement. Without decoupling, kinetic shockwaves transfer directly to the muzzle. This causes the sight picture to violently oscillate beyond the shooter's ability to track a target. 4 specific mechanical variables determine the efficiency of this biomechanical damping system. The first variable is knee and ankle angle. The degree of joint friction dictates how much impact shock reaches the shoulders. Second is contact time, the duration the supporting foot remains on the ground, reducing the window to regulate stability. Variable 3 is center of mass deviation, tracking shifts outside the parallel glide plane that skew aiming geometry. The final variable is trunk oscillation. If latitudinal tension drops, rhythmic leg swinging causes the upper torso to twist. These variables represent measurable kinetic failures. Unmanaged, they predictably alter the muzzle trajectory and cause missed shots. Internal stability is only half the equation. The shooter must also account for the geometry of a projectile fired from a moving platform. This introduces angular displacement. When a shooter moves laterally along the x-axis while firing at a target on the y-axis, they impart lateral momentum onto the bullet as it leaves the barrel. Because the bullet carries this momentum, the point of aim requires adjustment. The shooter must shift their crosshairs, offsetting the aim to ensure the final projectile vector intersects the target. The brain must also manage parallax. As the shooter moves, the optical perspective of the sights relative to the target continuously shifts, requiring constant updates to visual processing. Executing dynamic marksmanship requires the brain to simultaneously manage internal gait mechanics and calculate external ballistic geometry. Clinical testing protocols allow researchers to quantify the exact physiological and kinetic costs of moving while shooting. Heart rate variability is a primary metric. Acute physical stress increases ventilation rates, and the physical expansion of the lungs directly drives vertical shot dispersion, moving the muzzle in sync with the shooter's breath. Researchers also track gait speed, mapping the point where visual processing degrades and the eye can no longer maintain sight alignment. This diagram illustrates shot grouping density, measured through bivariate variable error. It plots horizontal range, vertical range, and shot group tightness to visualize deviations from the target center. Movement forces a clear expansion of this error cone. The data shows that the kinetic disruption of walking widens the shot group tightness circle, meaning accuracy drops as velocity increases. Every inch of movement adds a physical tax to precision. The data confirms that movement unconditionally degrades baseline accuracy. Clinical data often contradicts tactical training concepts, such as taking small, slow steps to get off the X during a close-range engagement. Tactical walking speeds allow a shooter to manage kinetic shock and hit a target. However, moving at this pace provides no defensive benefit. A stationary opponent can easily track a walking target. Moving fast enough to dodge rounds requires a full sprint. This speed destroys biomechanical damping and center of gravity control, dropping hit probability to 0. Even masterclass competitive shooters demonstrate this limitation. Pushing past tactical walking speeds leads to a breakdown in postural stability that shooting skill cannot override. Dynamic marksmanship operates as a zero-sum mechanical trade-off between kinetic stability and ballistic evasion. Precision shooting on the move is governed by the physical limits of the human skeleton.
Thanks for watching. Please like and subscribe to Logic Lab 77. And stay safe.